Welcome again on session on antigen antibody reactions, part 2. In this session, we are going to discuss a very important antigen antibody reaction, and that is called precipitation. Now, what we understand by a precipitation reaction. So, when a soluble antigen reacts with its antibody in presence of optimal temperature, optimal pH, and optimum electrolyte level, it leads to formation of antigen antibody complexes in form of either insoluble precipitate band if gel is there, or insoluble precipitates in liquid, or it will also form floccules if it remains suspended. So if it forms insoluble precipitate, we call that reaction as precipitation reaction. If it forms floccules, we call it as flocculation reaction. Now, why these precipitates they are formed, or how they are formed, or what is the mechanism of precipitation reaction? And the answer lies in Lattice hypothesis. Now let us understand this. According to Marek's lattice hypothesis, when the serum containing antibody is serially diluted and gradually the antibody levels it decreases as you go from this to this side, and a fixed quantity of antigen is added to such a set of test tubes containing serially diluted sera, then it is observed that antigen antibody reactions happens only in the middle set of test tube. Now let us understand with help of this graph. So we have a zone of antibody access in earlier test tube. As we go towards the last of test tube, actually the antibody titer is actually almost low, and their antigen access is there. So we call that zone as antigen access zone. And we have a zone of equivalence where antigen and antibody concentration, they are almost equal in proportion. So the zone of antibody access is known as Prozone phenomena, and zone of antigen access is known as Postzone phenomena. And we see maximum precipitation reaction happening in this zone of equivalence. Now, what happens in zone of antigen access or antibody access? That it cannot form a lattice due to inhibition of this lattice formation by excess antigen and antibody respectively. If you see the Prozone, you see that we have very less amount of antigen, so its binding sites will be saturated with a very few amount of antibody, and it cannot create a big lattice. The same thing happens with antigen access. Their antibody binding sites are saturated by this too much amount of antigen, and it cannot create a lattice. The lattice is only possible if antigen and antibody are in almost equal proportion. So this is known as zone of equivalence. And this phenomenon or phenomena are seen usually in natural infection also. Whenever a microorganism enters and creates an infection, so in early part of infection we have actually the antigen access. Then during the window period we have almost zone of equivalence, that is all available antigens, they can be complexed with the newly forming antibody. And lastly we have zone of antibody access, which is found in late part of infection when body has created an immune response and antibody try to overcome the antigen. So there are three phases, but the precipitation reaction happens mostly in the zone of equivalence. Now, what are the various precipitation reactions? Now we have a list of precipitation reaction, but we can classify them into two types. precipitation reaction in liquid and precipitation reaction in gel. If it happens in liquid, we have two types for it: ring precipitation test, and if instead of precipitate, the antigen antibody complexes, they remain suspended as floccules, we call them as flocculation test. And flocculation test could be performed in a slide or in a tube. So we have slide flocculation and tube flocculation test. Instead, if we perform precipitation reactions in gel, we call them as immunodiffusion procedure. And immunodiffusion procedures again can be divided into Oudin, Oakley, fulthorpe, Radial immunodiffusion, Ouchterlony, Immunoelectrophoresis, Electroimmunodiffusions and its varieties like Counterimmunoelectrophoresis, Radial electrophoresis, and Laurell's electrophoresis. Now, what are these that we will see one by one in this session. Now, what is a ring test? In this ring test, we take a test tube and we layer the antigen solution over a column of antibody, and then we see the precipitate at the junction of these two liquids where there is zone of equivalence in form of visible precipitates as shown in the diagram. Now, this test is very useful in grouping of streptococci, that is known as Landsfield grouping of streptococci. The another example is Ascoli's thermoprecipitin test done for anthrax. Then we have flocculation test, and in flocculation test we have first slide flocculation test, in which we take a drop of antigen on a slide, then we add a drop of antiserum or antibody on the slide, then we mix them by shaking, and the end result is the suspended floccules if the reactions has happened. And the examples are VDRL or RPR slide test, which are done to detect the antibodies against produced against the syphilis organism. The same thing can be performed in a tube. So we take a test tube, we take an antigen solution, we mix it with antiserum, and we see the floccules. And the example is again the Kahn test, which is used to detect the antibodies in case of syphilis. So this is the precipitation reaction in liquid medium in form of ring test as well as the flocculation test. Now, precipitation in gel, which is known as immunodiffusion. Why we needed that? Because it creates a visible and distinct band of precipitation instead of floccules, so it can be preserved for a very longer period of time. It can differentiate the individual antigens from a mixture, as each antigen will form a separate band after reacting with its specific antibody. We can also detect cross reactions and non-identity or partial identity or total identity between different antigens. So it gives us some advantage over the precipitation in liquid medium. So that's why the precipitation in gel has come up. Now, before I go into the types of immunodiffusion, you will see that the first type is Oudin immunodiffusion, or what we know as single diffusion in one dimension. Now, let us understand what is this diffusion and dimension. When we say that only antigen or antibody, they are moving, that means only one part is moving, we call that as a single diffusion. And when both antigen and antibody move towards each other, that is known as double diffusion. Now, what we understand by dimension, when a vertical diffusion is done on a tube, that is known as one dimension. It could be in either direction. But when we are taking a diffusion in both x and y axis, when test is done in either on a slide or on a petri dish laid with gel, we consider that as a two dimension. Now, having this in background, let us understand the first technique known as Oudin immunodiffusion, which is single diffusion in one dimension. Now, here what we do, we take a test tube, and when in that we put a antibody agar gel, and then we layer the antigenic solution over it. Now this antigen will diffuse towards the agar gel and will form a line of precipitation when there is zone of equivalence. Now second procedure is known as Oakley fulthorpe immunodiffusion, or what we know as double diffusion in one dimension. Now here again we take a test tube and we put antibody in agar gel, and above that we put a column of plain agar, and then we layer antigenic solution on top of this. Now what will happen, that antigen and antibody both will move towards each other, and that will create a precipitant band within the plain agar column. So both things are moving, antigen as well as antibody, so we call it as a double diffusion. But movements are only vertical, only in one axis. That's why we call it as one dimension. Then we have radial immunodiffusion, also known as single diffusion in two dimension. Here what we do, we take a slide or a petri dish, and we take antibody gel or anti-serum gel. Then we cut wells in it, we cut holes in it, and we put antigenic solution to it. Now what will happen, that this antigen will spread from this cut well into the antibody agar gel, and when both antigen and antibody are in zone of equivalence, we get a band, and that band will form a ring, because this is happening in two dimension. So we get a ring shaped bands of precipitation. So this is known as a radial immunodiffusion or single diffusion in two dimension. Then we have Ouchterlony immunodiffusion, or also known as double diffusion in two dimension. That is most widely employed immunodiffusion technique. Now here what we do, or how it is different from the earlier ones, we take a slide or a petri dish, we take plain agar gel here, okay, that is the difference, and then we cut the wells or holes using a template. Now in the central well here you put the antibody, and all the surrounding wells you put the antigen. And what will happen, this antigen and antibody they will move towards each other, okay. This antibody in the central well will diffuse, same way the antigen will also diffuse from their wells, and when this antigen and antibody will meet, they will create such bands. Now if bands intersect each other and form a X, that means those antigens are not related to each other. This is known as reaction of non-identity. But instead, if they form a inverted Y, or form a spur, that means it is a partially identical antigens are there. But instead, if they form an arc, that means they are in total identity. So we can also know whether the antigens are related to each other or not. The example of this test is the ULX gel precipitation test, which is done for detection of toxins which is produced by Corynebacterium diphtheriae. Then we have Immunoelectrophoresis, or precipitation gel in presence of electric current. Now problem with the earlier immunodiffusion in gel is that antigen and antibody, they move very slowly in the gel, hence it takes several days to finish the procedure. Now this movement can be made faster if immunodiffusion is carried out in presence of electric current, and that's why we have come up with this technique, Immunoelectrophoresis. Now here what we do, we take a slide on which we put plain agar gel, and then we cut two things, a trough as well as a well, as shown in the diagram. Then in the well, we put the antigenic solution, and then these antigenic components, they will separate it by electrophoresis. Then we fill the trough with the antibody, and this antibody now will diffuse towards the separated antigenic components, and when it meets with the antigen, it will form a precipitation bands. So we get a separate precipitation line between each antigenic component against its antibody. So this is the immunoelectrophoresis pattern of normal human serum comparing with the patient. So NHS stands for normal human serum. This is the patient's serum. Now see that there is an abnormality or bowing of this precipitin line of patient serum with certain anti-immunoglobulin isotype antibody, for example anti-gamma as well as this anti-mu or kappa. Same way, this is the second scenario. Now you can look for yourselves that which one is banding or bowing. Continuing the immunodiffusion used with electric current, we have developed electroimmunodiffusion also, in which there are three techniques. The first technique is Counterimmunoelectrophoresis. So here what we do, we take a slide, we put a plain agar gel on it, we cut the wells, and in one well we put antigen, and in another well exactly opposite to it we put the antibody solution, and while they are moving towards each other, we simultaneously do also electrophoresis. Okay, so this is known as counter current immunoelectrophoresis. It is used to detect alpha fetoprotein and cryptococcal antigen. The second is rocket electrophoresis. It is one-dimensional single diffusion. So it is used for quantitative estimation of antigen. So what we do, we take a slide, a square slide, in which we put antiserum and agar gel. So we take an antibody gel, we cut wells in it, and we put the antigen solution in increasing concentration, and then we do electrophoresis. Okay, now what will happen, this antigen will move towards the antibody along with this electric current, and as per the concentration you will see the different heighted bands, and by using the control bands as shown here of known heights and known concentration, we can measure the height of our taste band, and by plotting a graph we can know that okay, how much amount of or how much concentration of antigen is there. So we can do a quantitative estimation of antigen. The last procedure is in electroimmunodiffusion is Laurell's two-dimensional electrophoresis. Now here what we do, we take a slide on which we plot antibody gel, we cut a well containing the antigen. Now here this antigenic mixture is separated in a direction perpendicular to the final electrophoretic current. So first we give electric current in this direction, so antigen will be divided into its antigenic subcomponent, and then we supply the electric current in this direction in the second stage. So these subcomponents will move towards antibody gel and form the precipitin arc based on their concentration. So it is the Laurell's two-dimensional electrophoresis. Now let us take some questions which has been asked in past few exams, like Prozone phenomena is. So now we know what is a prozone, what is a postzone. So prozone is basically zone of antibody access. Again, Prozone phenomena is due to excess antibody. Which immunoglobulin class is the most efficient to produce precipitation reaction? Now precipitation reaction is best given by IgG antibodies. So yeah, Ring taste is used for, we use ring taste for streptococcal grouping by Lancefield technique. So it is a precipitation in a liquid. VDRL taste is an example of, now we know that VDRL taste, it is used to detect antibodies against syphilis, and it is a slide flocculation taste. So yes, it is a flocculation taste. Radial immunodiffusion can be used to estimate the following immunoglobulin classes. Now with help of radial immunodiffusion or precipitation, we know the best antibody which will give the precipitation reaction will be IgG, that we have seen in the last question. But here that does not mean that it cannot detect all other immunoglobulin classes. It can detect all the immunoglobulin classes. Countercurrent or counterimmunoelectrophoresis is used for detecting any antigen. It can almost detect almost all the antigens. It is based to detect antigens. So we will continue this antigen antibody reactions sessions in part 3 with agglutination reaction. Welcome again on session on antigen antibody